So the warm-up questions over there are calculus problems of functions that we've studied in pre-calculus. And so now we're going to transfer our ideas to performing the calculus, like derivatives and integrals, on this time parametric curves, equations of x and y, and then trying to do stuff like find a derivative, find areas under the curve, find arc lengths, and things like that. So I think we had this same screen last time where I started to introduce this and we ran out of time. So here is a reintroduction of the derivative. So we look at this as generally the slope of our tangent line. And in finding the slope of our tangent line, we should be able to find our equation of the line tangent to the curve. All right, so this is the formula. It's basically, it looks like simple algebra fraction that you cancel the dt's and stuff, but in general we don't want to think of it that way, because when we start dealing with partial derivatives, it's not going to work out the same way. Okay, so don't think about this as canceling the t's. Think about this as two completely different entities, formulas that are separate, that don't cancel out. All right, so I think it's better if we just jump to an example. Let's take a look at an example. And I think I picked a few problems from this. We'll start with number 4. So let's take a look at this. And then I have a graphing program that costs money for you to try to obtain. So if you want to purchase it, I can let you know where it is. But I'm going to use that because, to me, it's the easiest thing to use. So we want to find the equation of the tangent, of the line tangent to the curve at the point corresponding to the given value of the parameter. So we have t cosine t, t sine t, that's your x and y, and then you have t is equal to pi. So that's like your given value at a particular point. So to find an equation of a tangent is a line. To find an equation of a line, we need a point and a slope. So let's find the point. And the point is going to be given by putting the t into the x and the y value. So in symbols and notation, we would consider, not putting a t in there, but putting specifically a pi, which is the point in question that they have. And so if I put a pi in there, cosine of pi, does anybody know what cosine of pi is? -1, and then t is equal to pi, so this is negative pi. And then sine of pi is 0, so this whole thing is 0. We have a point, now we need a slope. And our slope is given by that formula again, so to find our slope, we need to find dy dx, which is going to be a y prime, or dx, or dy dt, is it? Divided by dx dt, which we have to find from this set of equations. So I'll take my x value, or my x function, and find the derivative of that. And I see it's a product of two functions, t and cosine t. So let's take the product rule. Derivative of the first times the second, plus the first times the derivative of the second. And so we have our derivative there, and we need the derivative for y. Again, the product, so it's derivative first times the second, plus the first times the derivative of the second. And to find our derivative, we would just put the y prime on top and then the x prime in the bottom. But to find the slope, we need to actually evaluate this when t is equal to that number in question that we're looking at. In this case, it's pi. So we need to put pi in there. And I'm just going to take a look at this and let's see what happens when we put pi into the x prime and the y prime. So let's put pi in the y prime over here. Sine of pi again is what? 0 plus pi times cosine of pi is what? -1. And we'll do the same thing. So it's going to be -1 plus pi times 0. And so what's our slope going to be? So we got negative pi on top, -1 on the bottom, so I think it's just going to be pi. Right? So we have a point and a slope. So we're ready to put those two together to get our equation. Y minus y1 is equal to the slope times x minus x1. And most of the time they want your answers as y equals mx plus b, so just solve for y. In this case it's easy enough. Looks like y is equal to pi x plus pi times pi. So I usually like to, especially if we have a graphing, nice easy graphing calculator to use, I like to see the picture of this to make sure that we're on the same page as the work that we're doing. So let's get a visual of this. We have a curve, first of all, that we're defining. We want it to be around pi. So let me get this set up. And for this particular graphing calculator, this is actually called graphing calculator. The notation is for parametric equations look like this. I have to make a two-dimensional matrix or a 2x1 matrix and then define it like that with t's. And so the function was t times cosine of t and t times sine of t. And this doesn't give me very much here, but this is a graph from 0 to 1. So I want to go large enough so that I involve pi in this thing. So I can go a little, I can stop at pi, but I want to go a little bit further. So I can go all the way up to 2 pi. So I just draw this from 2 pi, and it looks like it's a spiral of some sort. So the next thing I want to do is I want to find out where this point is, negative pi comma 0. I would imagine that's somewhere over here, right? That's an easy enough point to look at. But let's actually see it. So now I have a little dot over here. Negative pi comma 0, which is where I expected it to be. And then finally, I'll go ahead and squeeze in the equation that we found. Y is equal to pi times x plus pi squared. And then I see that that line is, in fact, tangent to that curve that we were looking at. So it's nice to have a picture that's done quickly enough so that we can immediately look at it and appreciate it and then move on. So that's what we're going to do. We'll look at it, take a picture, put it in our notes, appreciate it, and let's move on. Any questions? Okay, second derivative, that's something you studied in Comp 1. That seems pretty important. What's second derivative used for? Concavity. So it tells you if it's positive or negative, it tells you whether it's concave up or down. and you know, the magnitude of it. If it's a large positive number, then it's really concave. There's this idea of curvature that we're going to study later on that deals with the concavity, not just the concavity, but how curved is it. And we'll take a look at that when we study vector value function. But in general, second derivative tells us the concavity. So let's take a look at the second derivative. So the second derivative is the derivative of the first derivative. Oh, I should have had you guys guess first. If you're dealing with a second derivative, it's the derivative of the first derivative. So the first derivative looks like this. dy dx equals dy dt divided by dx dt. Now imagine, let's take the derivative of that. If you were to take the derivative of that with respect to x now, this is the tricky part because the functions are functions of t. And so when we're looking at derivatives at this point, when we're looking at derivatives, we're looking at dy dx, a derivative with respect to x. And so when we look at the second derivative, we also need to look at the second derivative with respect to x. So what we want to do is we want to take a derivative of this thing with respect to x. Now, I'll tell you what this is not equal to. If anybody's thinking about this, this is not equal to the second derivative of y with respect to t divided by the second derivative of x with respect to t. Because all that tells you now is that I've taken the derivative with respect to t, but the second derivative we're looking for is with respect to x. So I'm going to go ahead and cross this out to say that's not what we're looking for. Okay? So we want to express the second derivative as a derivative with respect to x. And so what we want to do is we have this derivative over here, and now we have to imagine taking the derivative of that with respect to x. So I guess some of you guys have already seen the formula, but this is a second derivative formula now. Let's take a look at this and use this for our notes. And notice it's slightly different from the stuff that was crossed out because we want to take the derivative of this thing with respect to x. So it's that dy dx, and the dy dx is this thing, and you want to take the derivative of that with respect to t, which looks like something over something. It looks like a quotient. Right? So it looks like we're going to need to get the quotient rule involved here. We're going to need to take the derivative of this thing with respect to t as a quotient of two functions of t. That's dy dt is a function of t, dx dt is another function of t. And then we'll divide that by dx dt. Yeah? We want our result to be a second derivative with respect to x, but the functions are functions of t. So eventually when we take the derivative, we need to take the derivative with respect to t. Yeah? Okay. All right, so, yes?
So the top part is the result of the quotient rule simplified, and then all of that is over.
Yeah. So we need to find dx dt, but we need to figure out what the top part is and then in doing that work, we're going to need to find the quotient rule. And let's see, as an example, number 8, hopefully that's a good one. For an example, let's take a look at number 8 on my list of finding derivatives and second derivatives and stuff like that. So we have e to the t and then t, e to the negative t are two functions, x and y. And they want us to find the derivative. So first, let's find dy dx. Which, remember, is y prime of t divided by x prime of t. I use switch notations on you guys. I hope that's okay, yeah? Is that okay? All right, so we're going to take the derivative. Looks like the bottom is easy, e to the t. The top is a product, so derivative of the first times the second plus the first times the derivative of the second. And normally we would be good with this if you were asked to find derivatives back in Calc 1. I don't know if your instructor did, but me as an instructor in Calculus 1, I say in general, don't simplify your answers. However, if you have to take the second derivative, usually you'd like to have an easier, more simplified answer before moving on. So it might be worth simplifying for us since we're going to need to find the second derivative. So let's do that. It looks like I can factor out an e to the t here, e to the negative t up on top, and then I have a 1 minus t up in the numerator. And then I have an e to the t in the bottom. Now, if you know your powers and your positive and negative exponents, I can bring this exponent down, or e to the t down, and then this will become e to the 2t in the denominator. So I have 1 minus t, e to the 2t is going to be a little bit easier to take the derivative of when we go into our next step than the original, two-term, one product rule up on top business, on top of a big quotient rule. So, in fact, most people probably would rather have this up on top, so they just have to do the product rule instead of a quotient rule. Oh, yeah, let's do that. Maybe I might rather do that. For all you quotient rule haters. So that's our first derivative. Now, our second derivative, they said, was d squared y over dx squared. That's supposed to be equal to the derivative d dx of, is it d dx or d dt? d dt. So d dt of our dy dx, which is this, divided by dx dt. Negative, thank you. Maybe I'll change the color on that. Too many strokes. So we have a lot of these components already, so let's just take the derivative of this thing. Now that we've arranged it so it looks like a product instead of a quotient, it becomes a little bit easier. Maybe, you think? E to the negative 2t times derivative of, so derivative of the first, I usually like doing the derivative of the first. Derivative of the first times the second plus the first times the derivative of the second. What was dx dt? Dx dt was just e to the t. We had that earlier, so I'll just write that down. All right. So to me, I'm kind of good with that. I wouldn't mind putting this answer over here and then submitting it because it should be algebraically the same. But here they ask for which values of t, is it concave up or down, so I have to solve for this where it's positive and negative, so I may want to simplify this again. So let's do that, since we're all algebra experts here, right? Yes. So it looks like I have an e to the negative 2t that I can factor out and cancel with e to the t. So I think that would just be, if it stays on top, it'll be e to the negative t. And let's see what goes in here. I have negative 2 plus 2t minus 1. I guess that's e to the negative t, 2t minus 3. All right, I did that right? I hope I did that right. Yeah?
Shouldn't, when you cancel the e to the t, should the negative t?
Should it? Probably. What do you think? So this is a positive down here. When you bring it up, it'll become a negative. Thank you. I think that'll work. All right. So that's our second derivative. Let's actually let's plot it and see, just for fun. I mean, not plot it. Let's check our answers. The first one, let's do the simplified version. E to the negative 2t 1 minus t. And the second one, let's do the non-simplified version just for fun. Are we here? Did I get my... All right, so let's see how complicated this is. E raised to the negative 2t minus 2, 1 minus t, plus e to the negative 2t times negative 1, and then we divide by e to the t. So I don't know if you guys are familiar with WebAssign, but they use Mathematica to parse your answer, and then in using Mathematica to parse your answer, generally they're able to tell whether this is correct or not by doing the simplification. And so if we decide that, okay, that's too long to write, I have it simplified here, so let's see, e to the negative 3t 2t minus 3. Let's see if we did our simplification correct and check our answer again. If we did the simplification correctly, then we should get a correct mark on this also. So it looks like the program will take either answer, and it looks like it's correct. Okay. So to check concavity, if you remember back from your old Calc 1 days, it's concave up if it's positive, if the second derivative is positive. So concave up if, I'll say y double prime, d squared y dx squared is positive. And so we're going to set this to a positive value. Basically set it equal to 0 and check where it's positive and negative. And if you remember our rules for exponential functions are generally always all positive, always positive. And so we can basically eliminate that. And so we can divide out by the exponential, and then we get t. I think if we just bring the t over, bring the 3 over, it becomes a positive, and you divide by positive 2, it'll stay there. So 3 halves. So using interval notation, I think interval notation is parentheses. So if we can type in our parentheses, how would you express this in parentheses notation?
Brackets or opening or
I think brackets are closed, so parentheses is open. So what do we want to type in if we're checking our answers?
or no, not open and closing, which one?
So I think we'll do the open one. So 3/2, comma, infinity. In nope. Yeah. Oh yeah, probably want open parentheses for that. So if you guys run into problems where they ask for interval notation, it's this parentheses, open, close, and all that stuff. And you can see some of the symbols that pop up on the right side of your text. All right, we good with second derivatives? So whatever this graph looks like when t, now this is a t, remember, it's not an x-axis, it's the t axis that you don't see in the drawing. Those are the places where it's going to be concave up. All right, let's go to our next topic. We're just moving along. Areas under the curve. So I'll take this in two parts. This is our formula for an area under the curve where you would have to find the antiderivative of something and then evaluate it from A to B. And so what we want to do is we want to find our analog formula by translating this formula into a formula that involves an x, or x of t and y of t. So this is essentially y, and this is essentially the derivative of x. So I guess in short, that's how the formula is going to translate. It's going to change that into y of t and then x prime of t dt. And so we need to integrate this as a function of t since our independent variable is t. So that's what the formula is going to give us. And here's our formula. And of course, the a and b will have to change accordingly. We're not dealing with x is equal to a and x is equal to b as limits in the x-axis. We're transferring those ideas to some values that start and end as t values.
Where does it mean when it says 1 to 1?
What's 1 to 1? You guys know what 1 to 1 is? For each input, there is only one output. That's half of it. For each input, yeah. For each output, there's only one input. So what you said defines a function. For each input, there's exactly one output. So that's a function. And now on the other side, for each output, there's only one unique input. And so you see those pictures of the drawings of these Venn diagrams and stuff, right? So for each input, there's one output. And for each output, there's one unique input that gets it. And so that's what makes it 1 to 1. And the idea that this is 1 to 1 just makes sure that you don't, the y value doesn't come back on itself. Right? What's that mean? Try to imagine that. The y value doesn't come back on itself. Or the x values doesn't come back on itself. All right, well, you guys can think about that. So this is going to give us a nice, easy translation. This is probably second least most important formula in this class. Don't use it very much, but I think it's just fun to to see how our Calc 1 and 2 ideas are kind of moving on to our Calc 3 ideas. So I think it's fun to look at it that way. So now if we have a curve, like that spiral that we were looking at earlier, we might be interested in finding, oh, this is a good example where it's the x of t is not one-to-one. Because the x value is overlapping with itself. So maybe we'll make an example out of this example. Since we were talking about one-to-oneness and why it's important to have one-to-one. Do you remember what the function was for this? Thank you. Thanks. All right. So just as a note here, we can make an example out of this to say, note, going from 0 to pi, this is pi, by the way. This looks like it's going from 0 to pi. X is not one-to-one. X is not one-to-one. It looks one-to-one. Are you sure this is right? So cosine, x is cosine? Zero pi. Oh. So it looks like x is not supposed to be, x doesn't look like it's one-to-one here. And when we're finding areas under the curve, we're finding, whoops. If we're looking at this example from 0 to pi, finding the area, this is finding the area under the curve on the graph, like going to the x-axis. Our area here doesn't look like it's well defined because the x value goes from 0 to some positive value, and then it goes back to 0 again, so it's not one-to-one. So I don't want to say here that note that x of t is not one-to-one on the interval that we're looking at. It's actually from 0 to pi. It doesn't look like it's one-to-one from 0 to pi. And so finding this integral of the area under the curve is not defined. So area under curve is not well defined. So that's a little note that says x of t has to be one-to-one. All right, should we do an example? All right, let's do a quick example of this. 15 maybe? No, 23. So we'll do number 23. Where we have to find the function that goes in the integral, that's called the integrand, And then that's the first part of your problem here. And the second part is to actually find out the numerical value. And we'll just punch it in a calculator to find that. Do you guys know how to use a calculator to find numerical integrals, by the way? Okay. All right, so how we're going to do this. It looks like our formula just tells us that we need to find the integral of y prime of t, oops, sorry, not y prime, but y of t times x prime of t dt. So just following this formula, the only derivative I need to take is the x. So let's find dx dt, or x prime of t. And that is going to be 1 minus 2, derivative sine is cosine t. And then our y is equal to this. And so we have our integral from 0 to 7 pi as the integral of 1. What? Oh, are you simplifying already? 1 minus 2 cosine t. This is your y. And then your x prime is 1 minus 2 cosine t dt. Yeah, 1 minus 2 cosine t squared. I suppose if you were to do this by hand, you would FOIL it and then take the derivative or antiderivative one by one and put in the values. Yeah? Oh, arc length. This is not one-to-one in the interval, so this is not going to be a good problem. All right, why don't we just save this for the arc length then? Oh, that sucks. What should we do? Well, let's find an actual problem that deals with the area. Sorry about that. Scrap that problem and look for an area enclosed. How about number 21 here? Thanks for pointing that out. We might have gotten a negative number, and I would have been really confused. You too, probably. All right, let's try this one. Find the area enclosed by the x-axis. And the curve 5e to the t is your x, and then t plus t squared is your y. All right, let's try this again. So it looks like the formula is your alpha and your beta, and then your y of t, and then x prime of t dt. So I think I can easily get the x and the y, or the y of t is there, the x prime is easy. And now I just need to worry about finding this alpha and beta. So what we need to do is we need to think about, I don't know how this graph looks like, but I'm imagining that this graph will intersect at the y-axis, or at the y-axis, the x-axis, at the x-axis in a couple of places where it would allow me to find some sort of defined area in there. So the question is, what are these two places where they intersect? For every t, there's a unique x. That's a good sign. All right, so this is, in fact, one-to-one, so that clears our one important, maybe I should write one-to-one. Looks like the 1-1 might look kind of weird. 1-to-1. Maybe the 1-1 is clearer. All right, so we need to find out these values where they intersect the x-axis. What can you say about these values where they intersect the x-axis? Y is equal to 0. So let's let y equal to 0. And I think if we just factor, when you get t is equal to 0 and t is equal to 1, right? So those look like they would be good limits for us. So they will end up being our limits, alpha and beta. And the only other thing we need to do is find y prime or x prime. So let's find x prime of t. And then let's put it all into the formula. So we're looking at the integral from 0 to 1 of t e to the, t minus 2t, or t minus t squared, sorry. That's your y. Your x prime is e to the t, and then dt. And then your limits go from 0 to 1 as we found the intersections of those x and y values. Okay, so yeah, good luck. Go at it. So if you haven't met Wolfram Alpha yet, this is Wolfram. Helps us find integrals and things like that. Helps us find indefinite integrals, definite integrals. It's not just a calculator where you punch in the calculator and you get some value. It actually does a bunch of analysis of stuff. It gives us its exact value and its approximated value. And in some examples like this one, where it knows it's looking for some sort of geometric thing, it gives us a picture of what it is we're looking for. So here's our answer that you would probably want to put in your homework if you had this as your homework problem. If you didn't have Wolfram Alpha, what would you use to integrate this? What Calc 2 technique would you use to integrate this? By parts. So do by parts maybe a couple of times. You got t squared, so you let your u equal to t minus t squared a couple of times until it becomes constant, and then e to the t is the dv, so it'll antiderivative is still e to the t. So it'll be this could be manageable without a calculator, but if you have a calculator, why not? Okay. All right, so let's get to that actual other problem that we were trying to do that was done incorrectly, and that was the arc length. So we need a formula for the arc length. I don't know if you remember the formula for the arc length for functions like that one, y is equal to ln x or something. There's a formula for that, 1 plus f prime of x squared or something like that, all under square root.
Yeah, it was, where in S is the arc length, ds equals the square root of dx squared plus dy squared, or the square root of dx, or the square root of dy over dx squared plus 1 dx.
So for parametric equations, your arc length formula is a little bit different. Looks like this. And there's a nice proof to this if you read your book. You can look through it. Let me just give you a brief overview of the proof. So suppose that this is your function. This is your parametric curve being drawn out. What you would want to do is imagine just like all the integrals that you've done in the past and how those integrals of the discussions on those integrals started, you would start off by finding partitions. You would partition your t into different values, and then you would find the arc length of one of them. Now, if we partition this into different values and then connect them with lines, then we know how to find the length of a line, right? Do we? If you have 2 points, you can find the distance between 2 points. That's a line. That's the distance of a little line segment. So what we're looking at here is a distance between 2 points, essentially. So the distance is, what's the distance? The distance is like the square root of yi plus 1 minus yi squared plus xi plus 1 minus xi squared, or something like that, right? Is that our distance formula kind of look like that? Think about Pythagorean's theorem if you have to think about that, you know. But what we have here is really a change in y and a change in x, so that's like delta x and delta y, and that's delta x and delta y in here. And then now imagine those are functions of t, so like multiplied by d delta t or something. You'll see the proof kind of come about if you multiply this by delta t over delta t. The delta t in the denominator goes into the square root as a square, and so it becomes delta x over delta t squared, and so that's dx dt. It eventually becomes that. And then there remains a delta t out here that becomes a differential. So anyways, that's just a quick sketch of a proof of doing this. Again, if you want to look at this with more rigor, then look at the book. So let's do the example that we're supposed to work on here, and let's actually look for the length here this time, length of the curve. So what do we want to do? We want to look for x prime, y prime, and you just plug it in the formula, right? So it's just a bunch of plugging and chugging into the formulas. So let's do that. So x prime is equal to 1 minus 2 cosine t. Y prime is equal to 0, and then derivative cosine is negative sine. So let's make this a positive 2 sine t. And then we need to square that and put it all under square root. So we're basically done here. Just put this nasty looking thing in our calculators or in our Wolfram alpha. So if you work this out, there'll probably be a couple of sines and cosines that you can make equal to 1 somewhere along the line. You have to FOIL this out, so there's going to be a middle term that's going to maybe help or hinder whatever it is you're doing. But in any case, if you have time, energy, and you should mess around with this to see what you can get. But to actually put this in our calculator, if you guys don't know how to use your calculator, I should let you know just quickly how to find a numerical value of an integral using your calculator. And I know this is t, but when we get to our calculators, we're going to take this back into, because this is an integral of one variable, and so when we go back to our calculator, we're going to go back to our calculator and look at this as a function in itself of x, since our calculator reads x's. Unless you have a TI-89, in which case you can call it whatever variable you want. But for us, I need to change the mode back to function. And then I need to define the function here. and the function looks like this messy looking thing. And if you don't feel like simplifying it, then go ahead and write out this long-winded function. So make sure you put parentheses where it's appropriate, especially when you're dealing with multiple inside-out kind of expressions. And when you do the square root, it starts off with a parenthesis, so you have to make sure you remember to end that with a parenthesis as well. And whenever you hit sine or cosine, it automatically brings up another parenthesis. So I think I'm almost done here. And once I close that parentheses, that's my function on the inside. Okay, now I want to be able to go from 0 to 7 pi here. I don't really care about the height, although I might want to, just for the sake of making this look neat and pretty, I might want to have my graph include the height. But more importantly, I'm going to go to my window and I'm going to go a little bit less than 0, maybe a -1, and 7 pi, 3.1, that's like 7 times 3 is 21, so maybe if I go up to 30 or something like that, that should cover more than enough of what I need. And like I said, I don't really care about the maximum, but if I make the maximum, I don't know, 30 also. So I don't know if we necessarily need to graph this. But it looks like I didn't really need to go that high. But what I want to do is I want to go to calc. So second function and trace, the trace button. And I have a handful of commands that I can use to calculate things. And the last one over here, number 7, looks like it's an integral. So I'm going to click on 7. And then it asks you for the lower limit. And you can use the arrow to tab or to trace to the right. But I know my lower limit is 0, so I'm just going to type 0. And then my upper limit is 7 pi. So I can actually type 7 and then a pi. And I'll press enter. And then it'll calculate, and it'll actually shade in the graph that you're looking for also. But you don't really care about the shading. All you care about is the numerical value here. So 46.4 to 4 decimal places, 46.7771. Of course, you can use Wolfram alpha as well, but during a test, you can't use Wolfram alpha. So if you're going to have to do something like this on the exam, you might want to get used to using your calculator. Okay. Any questions? All right, should we check? Let's check our answer and see if we get it right. Except I don't want to type in that big long thing, so. What was it, 47? What?
46.7.
So hopefully we get this right and we can move on. Okay, so it looks good. All right, our last sort of Calc 2 or Calc 1, Calc 2 topic is if you take that curve and you spin it around, not we're not interested in the volume like you did most of what you did. I think the surface area became a special case of another special application of the integral in Calc 2, but this is the same sort of idea. Since we just talked about arc length, it seemed like talking about the volume, or not the volume, but talking about the surface area might be a nice complement to that. And what they do with that is they look at basically a bunch of cylinders that approximated your values. So this is what this formula is about. So again, it's just another formula, and we've kind of did our formula and then did a problem, and then I don't know if we need to do another problem with this. But this is a surface area formula in case it comes up in your homework assignments. Okay? So when they say y, of course, that's y of t, and then x of t and y of t, the derivatives go in here. So I wanted to make one more comment. I guess I should have done this when we were talking about arc length. But if you have, I'll go to another page so it doesn't look confusing. Relation between y equals f of x and parametric equations. There's a couple of problems where they ask you to find the Cartesian relation between x and y if you have parametric equations. And so I just want to point out that if you have a function that looks like this, you can easily transform this into a parametric equation by letting your x equal to x, or t, as your independent variable, and then your y equal to f of t. Okay? So all you're doing is you're changing your parameter instead of some parameter on the side over there that you're not visualizing. You're going to change your parameter into the x parameter, and that'll work like a t parameter as well. So that means if you have, for example, y equals ln of x as a function, and say you wanted to find the arc length of that from 1 to 4, for example, then you can use the formula, right? And the formula is just saying I need to take the derivative of each of these, square it, and put it under square root, add them, and then I'll be all set. So it looks like our x is equal to t, so the derivative of that is equal to 1. Our y is equal to ln x. The derivative of that is 1 over x, right? Is that right? Okay. And so if I wanted to find the arc length, it's just going to be from 1 to 4 of 1 plus 1 over x squared dx. And I don't know, trig substitution or something might help you with this integral. Okay. So if you remember, if this is in fact your formula, then our x prime is always going to be 1, and our y prime is going to be the derivative. So if you look back at the formulas of finding the first derivative, finding the second derivative, finding the area under the curve, finding the arc length, and all that stuff that was in the warm-up problems, if you want to translate that to this, what you're going to come up with is going to be all the you're going to come up with are going to be are going to be all the formulas that you studied in Calc 1 and Calc 2. Except Instead of f of x, you'll have f of t. All right?
You know, I just realized that the area under a curve thing is essentially just u substitution instead of u as t.
Yeah, just as simple. Okay, I think that's it for today. Next time we're going to start polar coordinates, and so we'll do another activity on the board using polar coordinate stuff.
The warm-up, you turn in the
Oh, yeah, just put it on the table here with your names on it if you want. That's totally optional. I don't encourage you to do that because I have to look through it. But it's extra points for your extra possible amounts to extra credit. So, yeah, like at the end of class, because